Hi, Physics 2. Mr. Janowski here. This is the second part of the Chapter 37 slides. So in the last part, we learned that, well, I don't want to give away the do now questions. We learned Faraday's law and Lenz's law. And in this part, we're going to keep going with those ideas and start applying numbers to those ideas. So once you add math to something, it starts to become a more powerful idea. And we're also going to be bringing back in some of the ideas we've learned earlier in the year, some of the older ideas that we learned earlier in the year, and bring it all together, which I always enjoy doing. All right, so let's get started with that. So, what needs to change to induce an EMF in a coil of wire? Well, I had been saying that you need a changing magnetic field to induce a current or to induce a voltage, an EMF, but that's not strictly true. What actually needs to change is the magnetic flux. So yeah, here's your formula for EMF. So EMF is equal to minus N times change in magnetic flux, delta phi sub B, over change in time. So what is the formula for magnetic flux? The formula for magnetic flux is phi sub B is equal to B times A, the area of the loop, times cosine of theta. And if you actually had N loops here, you could kind of do it all in one shot and say phi sub B is equal to N B A cosine theta. And what are the units of magnetic flux? The units of magnetic flux are, depends how you want to say it. I think it looks like Weber in English, but I believe the regular pronunciation is Weber, and the German pronunciation would be Weber. So let's go with Weber's. We should probably just say Weber's. So yeah, magnetic flux, its symbol is phi sub B. Its unit is the Weber, which is equivalent to a Tesla times a meter squared, because it's a magnetic field times an area. And it is a scalar. So direction is going to be important in these things, but this quantity is actually a scalar. So what are some of the ways we discussed of changing the magnetic flux? So there's a few different ways. One thing you could do would be change the magnetic field. This is like Faraday's original experiment for doing this. So by changing the strength of the magnetic field, that would do it. You could change the area through which the magnetic field is passing. So in this middle picture, by drawing this loop out of the magnetic field, we're effectively reducing the area of it that is experiencing the magnetic field. So the area itself isn't actually changing in this case, but the area that's getting a magnetic field is. And the last thing you can do is you can change the angle between the area and the magnetic field. So yeah, if you look at your formula for magnetic flux, B, A, cosine theta. So yeah, you can change B, that's this first case. You could change A, that's this second case. Or you could change theta, the third case, by changing the angle between those things. And remember also, when you measure this angle, you measure the angle between the magnetic field, so these red lines in this drawing, and the normal, the imaginary perpendicular to your area. So what's the angle between the magnetic field and the normal to the area is one way you might say it mathematically. Let me just emphasize this because I think this is tricky and important. So when your magnetic field is perpendicular to the area, your theta isn't 90 degrees. Your theta in that case would be 0, because this theta represents the angle between the magnetic field and this thing that is already perpendicular to the area. So you have to be careful when you're doing your thetas in these problems. So I put a link to Crash Course Physics. I watched this. This one's pretty good. I'm not a huge fan of Crash Course Physics, but this one was pretty good. I didn't like the way she handled the right-hand rule about halfway through the middle of this thing. But other than that, she did a good job of going through the topics that we need to know. So I'll put a link to this in the description. You might find this helpful. So let's get some more practice using Faraday's law and Lenz's law. So down here we have this current. We have a loop of wire, and we have a current passing underneath it right to left, and the current is increasing. So we need to figure out which way the magnetic field is pointing. So do your grip rule. Hold your right hand out in front of you. Point your right thumb to the left, and notice that above this wire, the current's going to be going into the page. So into the page is our answer to the first one. Is our flux going to be increasing or decreasing? Well, if the current is increasing, the magnetic field is going to be increasing, and therefore our flux is going to be increasing. And then part 3, we have to use Ampere's right-hand rule to determine which way the induced current must flow to create the necessary magnetic field. Okay, so this increasing current down here is giving us more flux going into the page, which means we need the current that is induced to create a magnetic field that comes out of the page. So what is going to do that? It's actually going to be a counterclockwise current. So yeah, hold your right hand out in front of you and do the grip rule and figure out which way the current needs to go around this loop in order to get magnetic field out of the page in the middle of the loop. And you'll find that it needs to be counterclockwise. So some more practice. So this time we have a current passing left to right above this thing. So which way is the magnetic field pointing? Is our flux going to be increasing or decreasing if this current is decreasing? And then which way is the current going to flow through the loop? So I'm going slowly. I'm giving you time to think of your own answers. So pause it if you want to figure this out for yourself, because I'm going to give you the answer in 3, 2, 1. Yeah, this current is going to create a magnetic field into the page. It's going to be the magnetic field, the flux is going to be decreasing because the magnetic field is decreasing. And so the magnetic field into the page is decreasing, which means we need magnetic field going into the page from our induced current. So that's got to be going clockwise. So in this case, which way is the magnetic field pointing? Right hand rule, hold your right hand out in front of you, point your thumb down, and notice that to the left of your thumb, it's going to be going into the page again. So is our flux going to be increasing or decreasing? Well, if I is constant in this case, so the current's not changing, the flux is not going to change either. The flux is going to be constant. That means there's not going to be an induced current. So no induced current. And one more example of this. So now we have a current flowing top to bottom to the left of our loop. So hold your thumb out in front of you, point your thumb down, hold your right hand out in front of you, point your thumb down, and notice that to the right of your thumb, which way do your fingers curl? They curl out of the page. And this current is increasing. So this current is getting stronger. So what does that mean? That means our flux coming out of the page is increasing, which means the induced current must create a magnetic field that's going into the page. That's the Lenz's law part of this. So which way is the current going to go to do that? It would also be clockwise. So yeah, hold your right hand out in front of you again and figure out which way the current needs to go through this loop to make that magnetic field going into the page. And you'll find it needs to go clockwise. So now we're going to do a long multi-step problem that actually applies some math to this stuff. So what do we have here? We have a 5 centimeter square. It's a coil of wire. There's 100 turns in this wire, and the resistance of the whole thing is 100 ohms. So this is at the edge of a 0.600 Tesla magnetic field. So this guy's right here, and we're going to apply an external force that's going to pull this thing out of this magnetic field, and it's going to be completely out of the magnetic field in 0.100 seconds. So we've got to figure out a few different things about this. So let's see. We need to do a step, So what are we looking for? Part A, what is the rate of change of flux? So remember, flux is phi sub b, and the rate of change of flux is going to be phi sub b over t, and we expect that to have units of Webers per second. So what is the EMF? The EMF, remember, this is just the voltage, but in this kind of context, we use this symbol. This is one way to write an epsilon. So epsilon is equal to question mark V. What is the current? We use I for current. Its units will be amps. How much energy does this take? So energy, but it makes more sense in this case to think about the work. Work and energy are, again, the same thing, and they both have units of joules. And then we need to figure out what is the average force. So we'll go through this one piece at a time. So first, what is the rate of change of flux? Okay, well, delta anything is going to be final thing minus initial thing. So let's look at the math we have here. So delta phi sub b over delta t is going to be phi sub b final minus phi sub b initial over delta t. Your formula for phi sub b is right here, ba cosine theta. So I've got this stuff. And now we're going to plug in the numbers. So b final. So we'll go back to the picture, when the loop is completely out of the magnetic field through the loop is 0. So b final in that case is going to be 0. The area, so I just did the math separately. If it's 5 centimeters on each side, this square, well, that's 0.05 meters on each side. So square that, and you get 0.00250 meters squared. And then cosine of the angle. So again, we have this idea. When you measure the angle, let me go back to the other picture. So this magnetic field is going into the page, and our loop is in the plane of the page. So you might be tempted to say, well, the angle is 90 degrees because these things are perpendicular to each other, but that's not the way you measure the angle in this case. Because check out this picture. You measure the angle from the perpendicular to the area. So even though the magnetic field is perpendicular to the area, that theta is not 90 degrees, theta is actually 0 degrees because we measure the angle perpendicular to the normal. So I'm guessing this might be a area of confusion for some people, so I keep emphasizing it. So yeah, you measure the angle from the normal to the area. So the fact that they're perpendicular means that your angle is 0. So yeah, you put in the numbers. Well, this whole first term is going to be 0 because we're multiplying by a 0. This other guy is going to not be 0. Don't forget to divide by the change in time, and you get this for your final answer. Minus 0.0150 Webers per second. If Simon were here, he would say Webers per second, but Simon ain't here. So what is the EMF? So remember, EMF has units of volts. So it's just going to be this formula right here. So this part's fairly easy now that we've done part A. So we just take our answer for part A and multiply it by n, the number of turns we get. Be careful with your minus signs. So our first answer was negative, but we're multiplying by another minus sign. So our induced EMF is going to be 1.50 volts. So what is the current? Do we have a way of figuring out what the current's going to be based on the things that we know? Well, we know the EMF, which is just the voltage. Look back at the question up here. Don't forget about this. We do know the resistance. So if you know voltage and resistance, can you figure out the current? Of course you can. This is just Ohm's law. So we're using VIR. V equals IR. That means I is equal to V over R. So plug in what you just figured out for EMF, which is V, divide it by the resistance, and we end up with 0.0150 amps. And by Lenz's law, this induced current needs to be clockwise. So think about what's happening here. Before this thing starts moving, or even while this thing is moving, you have magnetic flux going into the page because the magnetic field is into the page and the area is perpendicular to it. As this thing starts to leave this magnetic field, you're losing flux into the page. So that means the induced current must be creating more magnetic field into the page. So do your grip rule going around this square loop, and you will see that your induced current needs to go clockwise in order to create a magnetic field into the page to counteract the change in flux into the page that we're losing. I feel like what I just said is accurate, and yet is going to sound complicated. This stuff, it's tricky. It's a little abstract. So yeah, keep practicing. So now, how much energy does this take? And energy in this context is going to be work. So think of all the different formulas we've learned for work. Well, one of them is our definition of power. Power is work over time, which means work is equal to power times time. And from a few chapters ago, we learned PIV. So Joule's law. Power is equal to current times voltage. So if work is power times time and power is current times voltage, then work must be equal to current times voltage times time. So take the answers we have so far, and remember that this whole thing is going to take 0.100 seconds. Do all that stuff together, and you'll end up with a work of 0.00225 joules. So not a whole lot of work. Joules being very tiny, and this just being about 0.002 of a joule. And finally, what is the average force? So how can we get the force using the things that we know? So we're going to have to go back to a fairly old idea. So from Physics 1, our definition of work. Work is equal to magnitude of force times magnitude of displacement times cosine of theta. And this time theta represents something else because, yeah, why wouldn't it? Remember when we're doing this formula for work. Work is equal to FD cosine theta. Theta is the angle between the force you have and the displacement. So remember, our force is to the right, and this thing is moving to the right, so it will be displaced to the right. So in this case, theta equals 0 represents the fact that our force and our displacement are in the exact same direction. So that's why this theta is going to be 0. So anyhow, work equals FD cosine theta. Solve that for F. Plug in your stuff, and you end up with a force of 0.0450 newtons. So, yeah, we even brought in one of the old Physics 1 ideas. So, to review, what are some of the ways we discussed of changing the magnetic flux? Well, look at your formula for magnetic flux, and you can change this thing, you can change this thing, or you can change this thing. So you could change the magnetic field. By closing the switch, you're going to have a changing magnetic field. So that would be one way of changing the flux through this loop. You could move your loop out of or into a magnetic field, which would change the area that's getting the magnetic field. So that's what we did in most of this part of the slides. And the last thing you can do is you can change the angle between your area and the magnetic field. So hopefully you guys are getting okay with Lenz's law. I really wish we were there in person to talk about this and to do all the right-hand rules and think about the fluxes and deal with all the problems in person that you might be having with this. But we're not there in person. We're here doing remote learning. Only a couple more weeks. We'll get through it. So anyhow, I hope you guys are finding this interesting.